Yep. April Fool's Day. You go. You want to start the attendance sheet around? So here we got questions from the homework assignment. Let's see. Number 6. Oh yeah, that's a fun one. Start off with 2 plane mirrors. You know what? I'm going to stop right here, and I'm going to move. So I've got plenty of room to work. So we've got 2 plane mirrors. Let me get the setup right. They are 2.3 meters apart. Okay. Inside this mirror, between these mirrors, you're standing right here, looking that direction. And you are, what, 1.6 meters? Yes. Away from that mirror. Okay. How far away from you are the first 3 images of yourself in the mirror in front of you? And are these images facing toward you or away from you? Okay, well, where's the first one going to be? It's going to be 1.6 meters this way. Here's the first image. And it's facing that way. Have you ever looked at one of these? Have you ever stood between 2 mirrors and seen that whole infinity-looking thing? You've never done that? Okay, well, find a carnival and try it sometime. It's kind of, I mean, well, you'll recognize it when and if you see it. Now, where is the next image? How far away are you here? 2.3 minus 1.6 in my arithmetic. So you're 0.7 meters there. Now we're looking for the next reflection you're going to see in this mirror. But that reflection isn't necessarily going to be of you. It is going to be, this is the only one that's actually a reflection of you. Everything else you see is going to be a reflection of a reflection of a reflection. So here you've got 0.7 meters. Which means 0.7 meters back here, you've got an image of you looking that way. And it is 1.6 plus 1.4 meters from here. So let me turn edge. And sign in and we give you some, return you some homework. Under turn edge. Make sure that's all. Yep. Is there. I'm gonna make sure I didn't stick somebody else's on the back of yours. Nope. There you go. Okay, so now, how far is it from here to here? It's 2.3 plus 0.7, so that would be 3 meters. Which means that is going to produce a reflection 3 meters this way. But it's looking away from you. That's the second reflection you're going to see. Now, what's the next reflection you're going to see and that is going to happen in this mirror? There's going to be a reflection of this image. And it is, let's see, that's 2.3 plus 1.6. From here is going to be 3.9 meters. Away from here. So 3.9 meters this way you're going to see a reflection of this facing that way. Now that means that 3.9 plus 2.3 meters is 6.2 meters. So 6.2 meters over here you're going to have another image facing that way. So, here is the first image, here is the second image, and here's the third image you're going to see. How far away from you are all of those images? Well, this one is 1.6 plus 1.6 equals this one is 3.2 meters away and facing you. This one is 3 meters plus 1.6, so this one is 4.6 meters away and looking away from you. And this one is 6.2 plus 1.6 is 7.8 meters away and facing you. Hey, Caleb Callison. Hoorah. There you go.
Thank you.
You're welcome. Any questions about how this worked? It's just a lot of keeping everything straight. Okay. Next question. Number 24, right? This one's fun. All right, number 24. An object is placed a distance r in front of a wall. Okay, here is the wall. Here is the object. This distance is r. So far, so good. And that r is exactly equal to the radius of curvature of a certain concave mirror. At what distance from the wall should this mirror be placed so that a real image of the object is formed on the wall? That means this is d sub I. We've got a concave mirror here that has a center of curvature r, right? Which means it has a focal length of r over 2. And it is placed at some distance d away from that wall. Now from here to the object, we know that that is d sub O. We know that f is the focal length is equal to the radius r divided by 2. And we know that d sub I is equal to d sub O plus r. Right? Now, you could also write this as d sub O is equal to d sub I minus r. Now, what do they want to know? They want to know this distance, which is equal to d sub O plus r, or d sub I. And if you start writing out the equations with the mind of solving for d sub I, then what you are going to do is you're going to end up deriving a very complex quadratic equation. You're going to have to plug into that formula and solve. And you will get, if you do it correctly, you will get the right answer. Let's look at what equations do we have here? We know that 1 over f is equal to 1 over d sub I plus 1 over d sub O. Right so far? I didn't throw away a negative sign somewhere, did I? Nope. D sub I is positive because it's a real image. D sub O is positive because it's in front of the mirror. So, 1 over F we can rewrite as 2 over R. Everybody see that? If F is R over 2, then 1 over F is equal to 2 over R. And that's equal to 1 over D sub O, the distance to the object, plus 1 over D sub I, which is simply D sub O plus R. So, just start multiplying through by stuff. Multiply through by D sub O plus R. We get, now let's just multiply through by R. We get 2 equals R over D sub O plus R over D sub O plus R. And now we can multiply through by D sub O, and we get 2 times D sub O is equal to R, that's an equal sign, R times D sub O cancels out, plus R times D sub O over D sub O plus R. And now if we multiply through by D sub O plus R, we get 2 D sub O times D sub O plus R equals R times D sub O plus R plus R times D sub O. Everybody still with me? So let's multiply, let's get rid of these parentheses, and we end up with R times D sub O plus R squared plus R times D sub O minus 2 D sub O squared minus 2 D sub O R. All right, now let's start canceling some of these out. We've got plus R D sub O here, plus R D sub O here is 2 D sub O, 2R D sub O, which we subtract out here, so we get rid of those. And we end up with R squared minus 2 D sub O squared is equal to 0, or R squared equals 2 D sub O squared. Take the square root of both sides, and we get R is equal to the square root of 2 times D sub O, or D sub O is equal to R divided by the square root of 2. Now that was pretty straightforward and painless. Trust me when I tell you this is a lot more straightforward and painless than solving for D sub I and going through all that quadratic nonsense. Because if you do that, what you end up with is D sub I is equal to r times 1 plus 1 over the square root of 2, or 1.707. This way you get r equals, or d sub o is equal to r plus r divided by the square root of 2. Problem is, read your question, read your problem. Your problem's not asking you for d sub o. Your problem is asking you for d sub I. Well, what is d sub I? D sub I, the distance to the image, is d sub o plus r, right here. Well, in other words, d sub I is equal to r, it's equal to d sub o, which is equal to r divided by the square root of 2 plus r, which is equal to r, that's an r, times 1 over the square root of 2 plus 1, which is exactly what you would have gotten if you had plugged in, if you'd have gone through the long way around and solved for the quadratic formula to solve for d sub I correctly. Okay. The difference is, by solving for d sub o instead of d sub I directly, you avoided that whole ambiguity of what's going on, why am I getting a second solution? And then having to sort out that, oh wait, that's a negative d sub o, which would not be possible. All right. Well, that means that d sub I, r times 1 plus the square root of 1 over the square root of 2, is the distance away from the wall that you would place the mirror in order to produce a real image on the wall. Now, is there any more to this question? Oh, yeah. What is the magnification of the image? What's the magnification? Does anybody remember the formula for magnification? It's going to be h sub I, the height of the image, divided by the height of the object, which will also be equal to I think that's right. I just want to make sure. Yep, negative d sub I over d sub o. Now, in this case, d sub I, here, let me make some room. D sub I is r times 1 plus 1 over the square root of 2, and d sub o is just r over the square root of 2. Which is equal to, this is m, which is equal to the square root of 2 over r times, keep the minus sign, r over 1 plus 1 over the square root of 2. Negative square root of 2r times 1 plus 1 over the square root of 2, all divided by r. These cancel, so we've got negative square root of 2 times 1 plus 1 over the square root of 2 equals negative square root of 2 plus 1. And there's your magnification. What does the negative sign mean? Nope. Makes it inverted. You'll have a real image on the wall. You will actually see the image on the wall, but it will be upside down. It'll be inverted. What does it mean if you have a positive d sub I? Chad, remember? Do you remember? I'm sorry. Hey, you? Do you remember? Colton Mashburn. Who is Chad? Show me a Chad. Pick a Chad, any Chad. Oh, he's not here. Yeah. All right. All right, I'm just going to do this for fun. Okay, I've got you, Colton, Caleb, Bettis, Jacob Bettis. You're Jacob Bettis. All right, you know what? Bite me. All of you. What is your name, man? Dwayne. You're Dwayne Lee. Okay, you're RJ Darnell. You're Hunter Turnage. You're Evan Beecham. Okay. Spot me a couple of you, and I can pretty well work out the rest. All right. Say again? Not really. I know who he is. I recognize him, but I'm only just now starting to associate names, which is, like I told you 13 weeks ago, would be just in time for it not to matter no more. No, that's Dr. Sullivan's bailiwick. I took 2 classes of chemistry in undergraduate school. I thought, oh, this is going to be easy. It's Chemistry 101. This is an element. This is another element. No. It's all memorization. I like what Enrico Fermi said when someone asked him, what he had against high energy physics and all that standard model and stuff. He said, man, if I wanted to memorize all those names, I'd have become a botanist. And that's pretty much chemistry. It's just it's like going into the medical field. It's just rote memorization. And as you can tell by my stellar work with your names, me and memorization don't get along well. Thank you. Do we have any more questions from the homework? Oh, did I get an answer on what the negative d sub I would mean? Say again? That means it's a virtual image. Specifically, it means the image is formed or appears to be forming behind the mirror. What would a negative object distance or d sub O mean? That would mean you're doing the problem backwards, because all of this is ray tracing. And you can trace the ray. It doesn't really care if this is d sub I and this is d sub O or vice versa. If you have a solution with a negative image, with a virtual image forming behind the mirror for some object position in front of the mirror, then a negative object position behind the mirror would just produce the positive real image in front of the mirror, if you could get light rays to pass through the mirror. And so that's what happened on this problem here. If you solved for d sub I directly and you went through and did all the quadratic formula, you would get 2 solutions. One would be d sub O here and d sub I here. The other would be d sub O back here and d sub I up here in front between the focal point and the mirror. So was that that was all the questions you had from the homework? Has everyone done the homework for last week? Yeah, all right, excellent. Well, we talked about index of refraction, was where we left off last time. Who wants to give me a refresher statement on the index of refraction? The whole speed of light thing. Well, it's a big chunk of it, if not the whole thing, but yeah. What is the speed of light? Three times 10 to the 8. What? Meters per second. Why do we use the letter C to denote the speed of light? No. It is in a vacuum, but we haven't gotten to that yet. Exactly. That's exactly why we use C, because Einstein was working out the issue of, is light, is it a wave or is it corpuscular? Now, I don't think we're going to get to it in this class, but if we did, we would get to what's called the slit, or the slit diffraction, where you shine a light, you shoot a light through a double slit. And the result is that you see this pretty wave pattern of bright and dark spot, light pattern on the back wall that you shoot it up against. Well, if light is made up of discrete little particles, or if it's corpuscular or particulate in nature, then you won't get that wave pattern. The only way you'll get that diffraction pattern is if light is a wave. If it's particulate, you're not going to get that pattern. But then Einstein came along and showed that it's also particulate. There are discrete little pieces of light that you can't have a part of, and he called them photons. He did the experiment was called the photoelectric effect. That's what he won his Nobel Prize for. And he then went on to work on his theory of relativity that everyone thinks he won the Nobel Prize for. And all he did when he did relativity, if you'll recall from last semester's physics, relativity was introduced initially by Galileo. And we came up with Galilean relativity, where how fast something seems to be going depends on how fast you're going relative to it. It's called Galilean relativity. It's what Newton was working with whenever he worked out his laws of motion. And it was the wholly, completely accepted understanding of how the world works right up until the end of the 19th century, when experimental results started just throwing big old honking monkey wrenches in everything. And there was a huge debate, a huge argument over whether or not light was particulate or wave nature. There was also a whole lot of argument about, why couldn't we measure the speed of light? Why did it not seem to behave the same way as everything else, according to relativity? That it seemed to everyone else that if light is moving along at this speed, and you're moving at this speed relative to it, then the speed you measure it at should be the sum of your two speeds. The whole Galilean relativity thing. Well, experimentally, what we discovered was that it wasn't anything like that. It didn't matter what your frame of reference you measured it from was. It didn't matter how fast you were moving relative to the source of the light or anything else. The speed of light was always measuring at 3 times 10 to the 8 meters per second, or 186,000 miles per second, or whatever that is in furlongs per fortnight. But the point is that it didn't matter what frame of reference you measured it from, it always came out the same, and that just defied everyone's understanding of everything. Then Einstein came along and said, okay, but it is what it is. And that's the whole point of the scientific method is you have experimental confirmation, you don't deny it. So what would be the consequence if the speed of light is a universal constant, which is where he got C, and that's why C is what shows up in that famous equation E equals mc squared. Back to optics. Speed of light is a universal constant. Under what condition? When it's in a vacuum. If this light is traveling through any other medium, its speed is no longer c. It's something a little bit less than c. In air, I think it's like 3 out in the 4th decimal place. It's 0.9997 times 3.8 meters per second. In other things, not so much. In water, I think the speed of light in water the speed of light in a vacuum is like 1 1/3 times as fast as it is in water. Or in other words, in water, it's about 2/3 its speed in a vacuum. In glass, it can be, the ratio of the speed of light in a medium Did I do that backwards? Yeah, I did that backwards. And that's in water. I don't know how many zeros, 2 or 3. There are enough zeros that it isn't going to matter for us because we're just going to use 3 times 10 to the 8. So the speed of light, the universal constant, the speed of light in a vacuum, is 1.33 times as fast as light traveling through water. It's just a hair faster than light in air. Diamond, it's like 2.5 times. The glass depends on the glass. Some of them 1.5 is generally a good guess for most glasses. These are called N. These coefficients are called N, which are the index of refraction for these materials. So N is equal to the speed of light divided by the velocity in whatever medium you're talking about. That is the index of refraction. And we talked last time about it. The law of refraction is that the angle of incidence and the angle of refraction are related how? Nope. The angle of reflection is equal to the angle of incidence.
Based on the end of the material.
Yeah. I just want to make sure I don't transpose something when I write it. Well, it brings us to this. The difference depends on the speed of the light. So the light that refracts in gets slowed down, going from a medium where it has a lower index of refraction to a higher index of refraction. It gets slowed down and it bends toward the vertical. This is important. Make a mental note of this, because it's probably contrary to what every trig class or geometry class you've ever taken. The angle is measured relative to the vertical, not the horizontal. Okay? But if we take the index of refraction of the two mediums, in the medium 1, the index of refraction times sine of the angle in that medium will be equal to, so the index of refraction times the sine of the angle in that medium will equal the index of refraction times the sine of the angle in the second medium. Or so let's look at what happens as a ray of light is passing through a pane of glass. You've got a ray of light coming in at this angle theta. In here we have a pane of glass, so theta 2 is going to be less than theta 1, or theta refraction is less than theta of incident. And it's going to pass on through to here, where this theta 2 is now the angle of incident. But now it's going from a medium with a higher index of refraction to a medium with a lower index of refraction. So it bends back out with a new theta refraction. Well, you can't really see it well here because I don't have calibrated eyeballs. But these two rays are perfectly parallel, just slightly offset. Or actually, I guess I drew that on the wrong side. Told you I'm not very good at that. Let's just let's work this out. Okay, I'm on page 658, example 23.8. We're going to just put some numbers to it. Refraction through a flat glass. Why don't they give us for the angle of incident there? 60 degrees, all right? That's in air. All right, so we have essentially 1 times the sine of 60 degrees will be equal to, we're going into glass, so in here is 1, in here will be, what, 1.33? No, they're going to say 1.5, right? Okay. Oh, that's right. 33 is water. We're going to go 1.50 here. That means, now because we're going into a higher index of refraction material, the angle of the ray, the ray of light is going to be bent towards the perpendicular, towards the normal. So it's going to be a lower angle here. And we know that this angle theta is equal to sine 1 times the sine of 60 degrees. Or sine of theta is equal to sine 60 over 1.5. And if we solve that and take the inverse sine, and then take the inverse sine, we get theta r of 35.3 degrees. That means now we've got to calculate a new angle of refraction into air. So we've got 1.50 times the sine of 35.3 degrees will be equal to 1.0 times the sine of the new angle. And if we solve for theta angle, we end up with, somebody with a calculator. Who did it?
35.26.
No, that's over here.
60. Yeah, it's 60.
60 what? Degrees. But did you actually do the arithmetic, punch it into the calculator? Yeah, you get a 0.08, but that's from rounding error. Point is that you get the same angle coming out that you had going in. Which means that the light was just shifted. You've probably all seen this effect looking through glass. If you look through it at the edges, look at your hand through it, you can always see that there's a discontinuity in the vision there. In the book they talk about how it makes the depth of a pond look shallower than it really is. Water is always deeper than it looks because of this. There are, right here, page 656. On the left-hand column, table 23-1 is a list of indices of refraction. And indices is the plural of index, not indexes, or indici, or indexi, or any of that. It's indices. That being established, you can pronounce it any way you care to, because I'm not an English teacher. I point that table out to you because that just seems like the sort of thing that would look real nice on somebody's note index card come test time. Pass this around and start looking at it. That's a prism I got out of a fairly nice, expensive set of optics, binoculars, very large ones. Pass it around, start looking at it, see how much sense you can make out of what's happening to the light as it goes through it. While y'all pass that around and look, what do we know? We know that if you have two materials where you have N sub 1 and N sub 2, and we're going to assume that N sub 2 is greater than N sub 1. I'm sorry. You have your angle of incidence and your angle of refraction. And as long as N sub 2 is greater than N sub 1, then the light coming from here is going to be bent towards the horizontal. Okay? Now, of course, if you get theta sub 1 all the way down to horizontal, then the light is going to pass right straight through. Why? Why is it going to be unbent? What's the angle when it's perfectly perpendicular to the surface? Zero. Remember, it's important. We're measuring relative to the normal, not relative to the surface. So whenever it's perfectly perpendicular to the surface that the light is transmitting through, the angle theta is 0, and sine of 0 is 0, which means there's going to be 0 angle of reflection in here. So once you bring that down perfectly normal to the surface, the light will just pass straight through without bending. Of course, if you get just a little bit off of perfectly straight, then you start seeing the refraction build up. Now what happens if n sub 1 is greater than n sub 2? You're going from, let's say, glass or water into air. Let's water into air. Think about you ever been down in the pool or in the lake and you get down and look up towards the surface? What do you see? Come on, somebody, has anyone here been swimming? Okay, what happens if you lay down on the bottom of the pool and look straight up at the surface? See the waves on the surface, but basically you see a round light. And then once you get past that round light, everything just goes, you can't see through the surface anymore. Let's say here we have water, 1.33. And here we have air, 1.0. Now, as again, if you're looking directly straight through the interface, it doesn't matter. The light's going to pass right straight through. But now, as you increase your angle of incidence, what happens to your angle of refraction? Oh, it is? Yep, all right. Good enough. No, that's fine. Lost track of time. We'll pick up right here Wednesday. Actually, I'll see y'all tomorrow for lab. Does everybody have that makeup exam ready to turn in tomorrow?